All righty. We discussed that light can behave both as a particle and a wave. And one more time to remind you that we understand something is a wave if they interferes, and we also understand something is a particle if they have a momentum. So that's the main takeaway message from here. And we understood that light both has a momentum, light also can interfere, so it's a wave. So it's both. Now we come back to our previous question. We say that I understood light, but how about the electrons? You remember that electron and the proton, those were the main dilemmas, that how we can make sure that electrons are stable, it is not falling into the proton. So is electron also a particle and a wave? Electron is a particle that people knew for for quite a long time, but people tried to see that whether electron can also behave as a wave. So they started to do the experiment like this. They took a electron gun and shoot it into a nickel crystal, and they looked into the scattered electrons. So on the left-hand side, you see the picture. So this guy, it's actually electron gun. It shoots an electron. It comes to the nickel crystal. So you see that these atoms, these are the atoms of the nickel particles. So these atoms are periodic, right? And when it gets back, they try to detect that how much electron is scattered and in which angle. So the detector can move around a particular radius of a circle, okay? And they move and then see that at which position they have maximum scattering of electrons, okay? And then they notice the following, that electron only scatters at a very specific angle, roughly around theta equal to 45-degree angle. We have the maximum scattering of electrons. And if you move up and down, the amount of scattering it reduces. So this kind of principle, this kind of observation, it shows that electron is also interfering with each other. Like if you explain electron as a wave, you can only explain this phenomena, that why an electron will have a very high scattering rate at a particular angle and not at a different angle. Okay, so this is how people know that electron can also behave as an angle, as a wave. So, all right, electron can behave as a wave. So then what? Then people gave even a crazier idea. In 1907, de Broglie, he proposed that it's actually not about only light and electron. In fact, everything that you see around, probably all of them are behaving both like a wave and a particle. Everything behaves like a wave and particle. And it is true. So I talked about the interference, right? And you know that if I shine light through two slits, then it will create a interference pattern. So people tried to shine those two holes by electrons. So they actually shoot electron guns through two holes, and they see the same kind of interference pattern. Okay, so that's clearly an demonstration that electron is also behaving as a wave. And then people became even crazier. They started to shoot bacteria between two slits. Okay, I do not know how they did it, but they really did it. They shoot at bacteria and started to see that whether they see an interference pattern or not. And they really saw interference. Isn't it crazy? It is really crazy. So people really understood that what they were proposing is actually real. Like you can only see in case of bacteria probably because they are micro scale, but probably if I try to shoot you through the slits, probably I won't be able to see the interference pattern. So this means two things. One, everything behaves like a wave and particle. And secondly, it must something has to do with the mass of something. Let's say I told you that interference also works for bacteria, but interference doesn't work for us. So the only thing that actually isolates from us with the bacteria is that we have a heavier mass. That means if mass increases, probably our wave behavior reduces and particle behavior increases. In fact, that's the heart of it. When mass goes down, your wave behavior becomes more prominent. When mass goes up, your particle behavior becomes prominent. Okay. So people said that since everything is a wave and a particle, so we know that a particle has a specific position and also has a specific momentum. All right. So let me draw a wave. I said that everything could be a wave and a particle. So if I draw a wave, how it will look like? This is a wave. Okay. So this is x-axis and this is y-axis. Y-axis just indicates the amplitude and x-axis is the position. And we can say that this is your wavelength lambda, right? All right. So we can use the principle of wave particle duality and we can say the momentum of this wave is actually h cut divided by lambda. Okay, so if you have a specific lambda, I can easily work out what is the momentum of that wave. But now the problem is a wave like this, it extends from minus infinity to plus infinity. Okay, I did not draw the entire stuff. Well, I do not have the space, but you understand that if I start to draw it, I can actually continue it for infinity, right? I can keep doing that for any arbitrary dimensions. So this means that I may have defined a momentum of this guy, but if you ask me what is the position, where does it exist? Where does this wave exist? Can I pinpoint any particular position? I cannot, because a wave actually exists from infinity to negative infinity, right? It exists everywhere. There are also examples where wave does not extend to infinity. Wave rather is limited to a particular place, and it happens when you have a cavity. So let us say that you created a cavity, like you created a box, and this box may contain a wave like this, okay? Or it may contain a wave like this, okay? So these are waves which has a finite dimensions, right? And a wave has a finite dimension if you can create a cavity. Do you know of any cavity that confines a wave? Any cavity or any wave. It doesn't have to be electron wave. Say it again. The whole. Explain it a little further. Hmm. Yeah, that's true. I was actually looking for some very commonplace example that anyone can understand. Like if you explain it to a third grader, he or she will also understand. Can we give an example like that? What what could be a cavity? Remember that a cavity creates a wave and it creates a stationary wave, right? Have you ever seen a stationary wave? Where did you see? Guitar string, exactly. Guitar string. A guitar string, uh, is not infinite, right? So it is bounded by those two terminals, right? Then guitar strings creates a stationary wave. So this is a very good example of cavity. All right. Remember, the cavity does not mean that it has to be bounded by all the four surfaces. As long as you can bound a wave, that's called a cavity. Okay. Um, so guitar string, very good example for creating a cavity. So we know that if you take a guitar string, so this is your guitar, and we are looking at the string's status, and the string would vibrate as a stationary wave. So they can vibrate like this, or they can also vibrate like this, right? Or they can also vibrate like this. Okay, so these are all the examples of stationary waves. Okay, so now we know that wave wave can be infinity, but it is not necessary that wave always has to be infinity. Wave can be finite as well. Okay, and in fact, if wave is finite, we can specify the position of the wave much more precisely compared to an infinite wave. So if you take a cavity which is even more smaller, like this, then we know for sure that where is the wave. Wave can also be confined in a very small space, right? But the problem is, for these kind of waves, for these waves, what would be the wavelength? For instance, what is the wavelength of this guy? How would you measure? Let us say I give you the dimensions. Let's say this is L, and let's say L is just 1 meter. Then you might be tempted to say that, well, if L is 1 meter, then from this shape of the wave, I can say that the lambda is probably twice of the length. That means lambda is probably 2 meter. Okay, that's one way of saying it. However, if you look into the whole spectrum, if you look into the whole spectrum of it, then I will draw this wave like this. I will draw the wave like the following. Inside the guitar string, we have some certain wave, but outside the guitar string, we have zero wave, right? It's just a flat zero. Does everyone follow that? Why I draw it like this? Outside those terminal of the guitar, there is no oscillations of strings, so I just draw it flat. I draw it as a wave only inside those terminals, right? But what is the wavelength for this guy? That's actually can be answered if you look into the Fourier transform of a wave. I'll show you something. So have you heard about Fourier transform previously? Everyone? Okay. So Fourier transform can actually tell you that what is the frequency of something if you give their time domain behavior, or it can, if you give them a space domain behavior, they can tell you what is the corresponding wavelength. Okay. So let us say that you give a time domain behavior, which is shown by the left-hand side. And the time domain behavior is the following. It's always zero on the left-hand side and in the right hand side, but at the very middle, it takes a magnitude of 1. Okay. So if this is the time profile, then the corresponding Fourier transform of this guy looks like this. So you see that it has a wave, and we just converted from the time domain to the frequency domain. Now, if we squeeze it, let's say, instead of having a profile like this that extends from -1 to +1, and everything outside this boundary is 0, if we squeeze it even further, let's say we squeeze it so that it only becomes 1, uh, within a very, very small boundary. So keep this picture in your mind, that this is the corresponding Fourier spectral of a time domain behavior, which is only non-zero between -1 and +1. And now I'm going to make this pulse even more narrower. If I make this pulse even narrower, you will see that this Fourier spectrum is going to become wider. Okay, so let us see. Do you see this? I made the time domain behavior narrower. Okay, look at the corresponding um, wave. The wave becomes flatter. Do you see this? So this is the very basic nature of Fourier transform. If you make something very narrow in time domain, it is going to spread out in frequency domain. In the same way, if you make something narrow in space domain, it is going to spread out in wavelength domain. Okay. So I said previously that a guitar string is an example of a cavity, and I can make the guitar string very, very narrow, right? If I make it very narrow, that means actually I'm squeezing it into the space domain. If I squeeze this into space domain, then in the wavelength domain, it is going to be spread out, okay? Spreading out means it has actually many, many wavelengths, not one wavelength. Try to understand. When something spreads out, it actually means, I'll draw this spread out stuff one more time here. So my time domain behavior was this. Let's say this is the time domain profile, which runs from -1 to +1. This is the time, and this is the amplitude, and its corresponding Fourier transform looks like this. Okay. So this is the frequency domain. Let me write it F for frequency, and this is the amplitude A. All right. So it looks like that if your time domain behavior is this, then we have some particular frequencies. We also have some other frequencies, but look at those frequencies. They are actually relatively smaller compared to the center frequency, right? But once I make this guy narrower, if I make a time domain profile that looks like this, then in the frequency domain, this guy is going to look like this. It is getting flatter. And getting flatter means what? It means that it has many, many frequencies. Okay. Remember that in previous case, you can say that only the center frequency was very big. The other frequencies was relatively smaller. Okay. They were getting much and much smaller. But now the center frequency, and look at the side frequencies, all the side frequencies, they are not actually much smaller compared to the center frequencies. They have many, many frequencies. Okay. So this is what happens when things get flatter. Okay. Now it comes to the dilemma. We previously learned that energy is related to the frequency, right? E is equal to h nu. But now I said that if you make something very, very narrow in time domain, then it is going to flatten out in the frequency domain. That means it has many, many frequencies. So what would be the its energy? Do you understand the dilemma? If something has many, many frequencies, then you cannot really define what is the exact energy of it. Understood? So its energy becomes uncertain if you can define the time domain behavior. In a similar way, let me go back. So we discussed that if you can define the time behavior, if you can narrow down the time, then its frequency gets spread out. It obtains many, many frequencies. That means its energy cannot be very well defined, because E is equal to h nu can only be well defined if it has only one frequency, okay, not many frequencies. In a similar way, if you narrow down something in space domain, then its wavelength gets spread apart. Like it assumes many, many wavelengths. And if something has many, many wavelengths, then you cannot define its momentum properly, because momentum is related to the wavelength like the following equations. P is equal to h cut divided by lambda. So if something has many, many lambdas, you cannot properly identify what is its wavelength. Sorry, what is its momentum. So this is how people came into the idea of uncertainty principle, that momentum and position cannot be simultaneously precisely measured. There must be some certain errors. In a similar way, the energy and the time, they also cannot be simultaneously measured. There must be some minimum value of errors. And these are called Heisenberg's uncertainty principles. So given that, let's see, we have just 5 more minutes left, right? Huh, you guys are tired? Okay, good, good. You know, I mean, somewhere I heard that people's attention uh, cannot exceed more than 20 minutes. Okay, like no matter how hard you try, you cannot keep somebody's attention drawn more than 20 minutes. So this is how some people started to think that, okay, we will make something really short. So in my country, I came from Bangladesh, by the way. In my country, some guy, they thought that the school systems, they are getting very bored and inefficient because the class is very elongated, like 1 hour lectures, and no one can pay attention to that. So he came with the idea that, okay, instead of 1 hour lecture, what if we just give 10 minutes lecture? Okay, so they actually really started a business on that. And the name of that business is 10 minutes school. So everything, whatever you do, you have to finish it in 10 minutes. That's the idea. And it actually became very popular. I mean, there are pros and cons for, of course, everything. But I think maybe this is something that we should also keep in mind. I mean, we are living in a day of like social media and stuff. So our attention span doesn't really get very long. Um, Maybe we should start thinking about that. What could be other alternative of giving a hour-long lecture? Can we actually make it smaller? Can we burst it into small values? So anyway, until we get a good result, we have to torture you, unfortunately, for a little longer. So hope you bear with that. And by the way, we are getting really closer to solve the puzzle. Remember that the puzzle was that how do we know that whether atoms is going to be stable or not? Atom should not be stable. Electron must be collapsing to the protons. So there must be something that prevents electron from doing that. So we are getting very close to that answer. So based on we talked about the waves nature and particle natures of something, and we say that everything, including the lights, including the electrons, even the bacteria, they all show some kind of waves nature and also particle natures. And the waves nature becomes dominant for small particles when particles mass becomes smaller, and when particle mass becomes larger, the particle behavior dominates. So then in 1926, Erwin Schrödinger, he came up with his phenomenal equations of motions for particles that shows both wave behavior and particle behavior. Remember that before Schrödinger, in order to understand the particle behavior, we always resorted to Newton's law of mechanics, right? And that was very simple. But now Schrödinger came up and he proposed a different kind of equations in order to explain these um, interesting stuff of particle that behaves both wave and particle. So what is the general form of the wave that Schrödinger proposed? The general form of the wave that he proposed is something like this. D square psi by dx square equal to hmm. So this is the general wave equation. Man, I wish I was longer. I was taller. So this is the general wave equations. And it may look like very like alien. Like, what is this guy? I've never seen this, which is okay. Okay. So let me try to make it a little bit familiarized to you. Okay. When we say that, when we see an equation, how to make sense out of it? Okay, let's say, let's forget about these complex equations. Let's first start with the simple equations. Um, let us say um, I know a particle which moves at a speed of v, and I just want to know that after a certain time t, how much distance does it going to cover? Okay. So how do I use equations in order to find the solution? It's simple that the distance s is related to velocity multiplied by the time, right? Everyone understand this part. If something has a velocity and if you give them some time to propagate, then using this equation, you can easily find out that how much distance is covered by that particle. Okay, so if the particle does not move at a constant velocity, rather it moves at a constant accelerations, can I use this equation? If something has a constant acceleration, let's say that I'm looking at a particle that is falling freely into the ground because of gravity, then I cannot use this equation, right? S equal to Vt cannot be used. Rather, I have to use the modified equations, which is like this. S equal to Vt plus, do you know what correction factor I should put? What is that? Right, half a d square. So if I have these equation in our pocket, we can easily find out how much distance is going to be traveled by a particle, provided that I know what is the um, accelerations and what is the velocity, what is the initial velocity. Now let's look at a general form of equations. A general form of equation, how it may look like. Let us say I want to solve an equation that looks like this: x square minus x equal to 0. No physics here, just a mathematical equation. Okay, let's say that in order, I want to find out some particle state, and in order to know the state, I need to solve these equations: x square minus x equal to 0. What would be the solution of these equation? 0 and 1. How did you figure it out? Mm-hmm. Right. Right. So you can take x common, and then you can have two different term, and then you can say that, okay, these two term must be, either one of them must be 0. So this is how I know that either x is 0 or x is 1 or both, right? So this is how you know. Understood. Very good. Now there is, instead of taking the term x as a common, we can just use plug and play value, right? We can ask this question that x square minus x equal to 0. So that means we are looking for a number that remains same even after you make a square of it. You see this? It just said x square. It just said x square equal to x. They're same stuff, right? So we are really looking for a number that remains same after you square it. So there is only two numbers. If it can be 0, so square of 0 is same. And also if it is 1, then square of 1 remains 1, right? Now go back to the previous question. This apparently complex structure. This guy. What it is trying to tell? It is trying to tell the following. It says that in order to find the value of psi is a variable, okay? So in order to find the variable psi, how do we solve it? We have to find some value of psi so that if you take the derivative with respect to x, that means derivative with respect to position, and if you also take the derivative with respect to time, they are actually same. Think about this equation again. This equation was very simple, and we say that we have to find a value of x so that even after taking square of it, it remains same as the previous one. And now this equation is saying that psi is something so that no matter whether you take a time derivative or a space derivative, it's same. You see this? It's saying again, one more time, it's saying if you take the time derivative twice, or if you take the space derivative twice, it must be same. Okay. So question to you, are you run out of time? What time is it? 2:20? Oh man, no. We shouldn't exceed the time. So guys, let us start our discussion from the next class, and we will see that how to solve this equation. Okay. Thank you guys. Thank you for your attention.